In the last session, we were in the classroom workbook. We have finished question numbers from 1 to 10. Now we were in question number 11. So let us start this question with the classroom workbook from question number 11. What it is? The general solution of dy by dx equal to cos of x plus y is, options are given. Now let us try to solve this equation. Now it is dy by dx equal to cos of x plus y. When you try to expand this in the form like this, cos of a plus b is cos a cos b minus sin a into sin b. So when you apply this formula, cos of a plus b equal to cos a cos b minus sin a sin b, then between functions of x and functions of y there is a minus symbol. So we cannot solve this by separating variables. Even it doesn't come under method 2 also, that is homogeneous, right? Now let us try to handle this by using substitution method. So this is in the form f of ax plus by plus c. So a function of straight line, dy by dx equal to function of straight line. Now what is a value? 1, b value is 1, and of course c is 0. Therefore the f of z is what? Actually z is ax plus by plus c. So in this case my z is x plus y. So that means I am going to solve this equation by method number 3, that is substitution method. So we take z equal to x plus y, then f of z becomes cos z. Therefore what is the general solution of this equation? Its general solution is given by integral 1 by a plus b into f of z dz equal to x plus c. This is the general solution of substitution method. So this implies integral 1 by a value is 1 and b value is 1. There f of z is cos z. Now this becomes integral 1 by 1 plus cos z dz equal to x plus c. Now we have a formula for 1 plus cos 2a. What is the formula for 1 plus cos 2a? This is 2 cos square a. So if it is 2a, now it becomes a 50%. Now replace 2a by just cos a. So 1 plus cos a becomes 2 cos square a divided by 2. Now here a is z. So this implies integral 1 by 2 cos square z by 2 dz equal to x plus c. Now this implies 1 by 2 into integral secant square z by 2 dz equal to x plus c. This implies 1 by 2 into integral secant square z by 2 is tan z by 2 divided by z by 2 derivative is 1 by 2 equal to x plus c. This half will be cancelled. Therefore its general solution is given by tan of z by 2 equal to x plus c. But what is z? This z is nothing but x plus y. So therefore the final general solution is tan of x plus y by 2 equal to x plus c. Therefore option number D is right answer. Tan of x plus y by 2 equal to x plus c. So option D is right answer for this question. Note these points. So what it is? The general solution of dy by dx equal to x plus y minus 1 whole square. We need to find general solution of this problem. Now let us see. It is just like previous problem. So right side is a function of ax plus by plus c. Ax plus by plus c. Therefore, this must be taken as z. So what is z? X plus y minus 1. Now what is f of z? F of z is z square, because this is z value. RHS function is f of z. So it is f of z equal to z square. Here a value is 1, b value is 1. A is coefficient of x and b is coefficient of y. So its general solution is given by integral 1 by a plus b into f of z dz equal to x plus c. So this implies integral 1 by 1 plus z square dz equal to x plus c. Integral 1 by 1 plus z square dz is tan inverse z. So tan inverse z equal to x plus c. So this implies tan inverse of z is nothing but x plus y minus 1 equal to x plus c. So this is the general solution of this equation. Question number 13. Which of the following equation is exact? What is my option A? Minus y dx plus x dy equal to 0. Now this is m value. M is minus y, n is x. Now in this case, dou m by dou y equal to minus 1. Dou n by dou x equal to plus 1. So both are different quantities. So it is a non-exact equation. Dou m by dou y is minus 1. Dou n by dou x is plus 1. So it is a non-exact equation. So option A is wrong. Now look at option B. It is y dx plus x dy equal to 0. Now m value is y and n value is x. So in this case, dou m by dou y is 1. Dou n by dou x equal to 1. Therefore, when you verify option B, both dou m by dou y and dou n by dou x quantities are becoming same. So this is one of the exact equation. Therefore, for question number 13, option B is right answer. Just application of definition of exact equation. So when do we say that equation is exact? If dou m by dou y and dou n by dou x are same. In case of option A, they are different quantities, so it is a wrong option. Eliminate this. But when you look at option B, both dou m by dou y and dou n by dou x are becoming same. So this is an example of exact equation. So option B is right. Just verification. Next, we move to question number 14. The solution of one equation with initial condition is. So let us write the equation. Y e power x dx plus 4y plus e power x into dy equal to 0 with the boundary condition y of 0 equal to minus 1 is few options are given. Generally, the question is related to a particular solution. So when you are dealing particular solutions, try to verify boundary conditions. If only one option satisfies given boundary condition, it could be right answer. But when you look at options, these are not direct y values. In option A, we have y e power x plus 2y square minus 1 equal to 0. So combination of y along with functions of x. The same case with option B, C and D. So it may work, but instead of verifying this, better we can solve it directly. Let us try this. Now this equation is in the form m dx plus n dy equal to 0. So this is m value and this is n. So what is m? M is y times e power x. N is 4y plus e power x. Now this cannot be handled by using separating variables. Method 1 is not possible. Because between functions of x and functions of y there is a symbol plus, so we can't separate variables x and variables y. Even this is not a homogeneous function, because if you want to get homogeneous, you should not have you should not have functions other than powers of x and powers of y. Here we have exponential functions like this. Therefore homogeneous is not possible. So method 1 you can't apply, method 2 you can't apply. So even method 3 also you cannot apply, because this is not a function of straight line, because it has exponential function. So therefore method 1 is not possible, variable separable method. Method 2 is not possible, that is homogeneous, and even still method 3 is not possible. So let us try for method 4, that is exact model. So here dou m by dou y equal to e power x. Dou n by dou x is also equal to e power x. Now both quantities are same, so it is an exact equation. Now we can apply method number 4. So its general solution is given by integral m dx. What is m? Y e power x. So integral m dx with y as constant plus integral n dy free of x. Now in n we have two terms. One is 4y, another is e power x. Now this is the term of n which is free of x. So in place of n we can write 4y. So integral y e power x dx with y as constant plus integral 4y dy equal to general constant c. When y is constant, we can take outside y into integral e power x plus integral 4y dy is 2y square equal to c. Now this is my general solution. Now even you need not find the value of c in this case. If you apply this boundary condition, you will get the value of c. But for this question, even it is not required. Let us see. Because in the first option, we have y e power x plus 2y square minus 1 equal to 0. In the second option, before y square, we have x. So option B, you can eliminate. In option C, we have y e power x, but only minus y square is there. But this is plus 2y square, so it is wrong. In option D, we have x e power x, but coefficient of e power x is x, so option D also wrong. Therefore, option B is eliminated, C is eliminated, D is eliminated, so it is directly A. Or you can easily get the value of C, you will get C value 1. How to find this C value? Apply the boundary condition, x value is 0, then y becomes minus 1. So in that case, x is 0, y is minus 1. Therefore, this becomes minus 1 plus 2 equal to c. So c value 1. Substitute c value 1 here. We get y e power x plus 2y square equal to 1. This is my particular solution. Therefore, option A is right answer. Note this. Now with this we have finished 14 questions from classroom workbook. That means questions based on method number 1, method 2, method 3 and method 4, right? Now we move to a few basic definitions which are useful for method 5, method 6, 7, 8 and so on, right? Now let us start with a definition, that is integrating factor. Integrating factor. Let us see what it is. Suppose we have an equation mdx plus ndy equal to 0. If it is an exact equation, then getting solution of this equation is very simple for us. What is my task? Solving first order and first degree equations. If it is in the form mdx plus ndy equal to 0, if it is an exact equation, then general solution is very simple. Integral mdx with y as constant plus integral ndy p of x equal to c. Suppose if it is a non-exact equation, assume that this is a non-exact equation, then still this can be made an equation exact by multiplying this with a non-zero function of x comma y. We call it as mu of x comma y. It is a non-zero function. So this is a non-exact equation, but still this can be made exact if it is multiplied with a non-zero function of x comma y. Such a non-zero function of x comma y is called an integrating factor of this equation. So the basic purpose of finding an integrating factor is, it is very useful in converting a non-exact equation into exact equation. One simple task, I have a non-exact equation, but I want to get its general solution. So what is my task? Simply to solve first order, first degree equations. If it is an exact equation, my solution becomes so simple. But if it is a non-exact equation, but still this can be made an exact equation when it is multiplied with a non-zero function of x comma y. And such a non-zero function of x comma y is called an integrating factor of this particular equation. Sometimes it may contain only terms of x, sometimes it may contain terms of y only, sometimes it may contain both x and y terms. But a non-exact equation can be made an exact equation if it is multiplied with a non-zero function of x comma y, and such a non-zero function of x comma y is called an integrating factor of given non-exact equation. Write this definition. A non-exact equation can be made exact. A non-exact equation can be made exact when it is multiplied with a non-zero function of x comma y. A non-exact equation can be made exact when it is multiplied with a non-zero function of x comma y. Such a non-zero function is called an integrating factor of given equation. Such a non-zero function is called an integrating factor of given equation. Right? Now we discuss one basic example followed by the procedure to find integrating factors of non-exact equations. Right? Let us start with a basic example. That is y dx minus x dy equal to 0. Now let us see, in this case the value of m is y and n equal to minus x. So here dou m by dou y equal to 1, comma dou n by dou x equal to minus 1. So both are different quantities, so it is a non-exact equation. But I can make this equation by multiplying this with certain non-zero functions. Let me work out this. Suppose I am multiplying this equation with 1 by y square. In future sessions I will give clarification how to get this 1 by y square is an integrating factor, but for the time being just try to follow this, how this becomes an integrating factor. So I am multiplying this equation with 1 by y square. 1 by y square into y dx minus x dy equal to 0. So this implies 1 by y into dx plus minus x by y square into dy equal to 0. Now this is the latest value of m. This is 1 by y. And n is minus x divided by y square. So here dou m by dou y equal to minus 1 by y square. Dou n by dou x equal to minus 1 divided by y square. Therefore, when you look at this, basically this is a non-exact equation because both are different quantities. But when it is multiplied with 1 by y square, m values and n values have been updated. But after that, when you calculate dou m by dou y and dou n by dou x, both are becoming same quantities, minus 1 by y square, minus 1 by y square. Therefore, now this equation became exact because it is multiplied with 1 by y square. Therefore, according to definition of integrating factor, this 1 by y square is one of the integrating factor of this equation. I am saying that this is one of the integrating factor. That means it has a multiple number of integrating factors. I will discuss. But 1 by y square is one of its integrating factor, right? Now, even we prove that it has some other integrating factors. Let us see. Let us multiply this equation with 1 by x square. 1 by x square into y dx minus x dy equal to 0. This implies y by x square into dx plus minus 1 by x into dy equal to 0. So the latest values of m and n are y by x square minus 1 by x. Now in this case, dou m by dou y equal to 1 by x square, dou n by dou x equal to again 1 by x square. Now interestingly, both quantities are same, dou m by dou y and dou n by dou x. Therefore, this became exact even if it is multiplied with 1 by x square also. Therefore, this is another integrating factor of this equation. Now, let us prove that it has another integrating factor. That is, I will try to multiply this equation with 1 by xy. So, 1 by xy into y dx minus x dy equal to 0. Now, this implies 1 by x into dx plus minus 1 by y into dy equal to 0. Now, what is my m? It is 1 by x. N is minus 1 by y. So here dou m by dou y is 0 because it is a constant, and dou n by dou x is also equal to 0. So therefore in this case both dou m by dou y and dou n by dou x are same. Therefore this is another integrating factor. Therefore till this moment we have proved that this particular non-exact equation has three integrating factors. What are they? One is 1 by y square, and another one is 1 by x square, and last one is 1 by xy. Even we can easily prove that 1 by x square plus y square is again an integrating factor of same equation. It is simple to verify just like this. Therefore, from this basic example, one can conclude that a non-exact equation can have multiple number of integrating factors. Multiple number of integrating factors. Now, I have one doubt. What it is which integrating factor to be used to get the general solution. The basic purpose of integrating factor is it helps us to convert a non-exact equation into exact equation. Now, which is useful for me, even if you use 1 by y square or 1 by x square or 1 by xy or 1 by x square plus y square, the equation becomes exact. And apply method number 4 to get general solution of exact equation. Finally, solution will be same. See, I use integrating factor 1 by x square. Some another may use 1 by y square. Another person may use 1 by xy. Some another person may use 1 by x square plus y square. But all of our 4 people intention is to get the general solution. All must get same general solution. So it is immaterial for us which integrating factor is to be used. Is this clear? So therefore from this it is clearly understandable that a non-exact equation can have more than one integrating factor, right? Note all these examples. Now write the conclusion of all these steps. Therefore, 1 by y square, comma 1 by x square, comma 1 by xy, and 1 by x square plus y square, or integrating factors of y dx minus x dy equal to 0. This you can easily verify. So you write it as a part of integrating factor. 1 by y square, 1 by x square, 1 by xy, comma 1 by x square plus y square are all integrating factors of y dx minus x dy equal to 0. Note, a non-exact equation can have more than one integrating factor. A non-exact equation can have more than one integrating factor. A non-exact equation can have more than one integrating factor. Now, when you look at these points, in the first case, 1 by y square is my integrating factor. It is purely a function of y. It is purely a function of x. It contains both x and y terms. It contains both x and y terms, right? Now, let us discuss one standard procedure to find integrating factor of a non-exact equation. So the next concept is procedure to find an integrating factor. Procedure to find an integrating factor. We have 4 different cases. Let me discuss one by one. Suppose we have a non-exact equation m dx plus n dy equal to 0. It is a non-exact equation. Now let us discuss one by one. Case 1. Suppose if m comma n are homogeneous functions of same degree and mx plus ny not equal to 0 and mx plus ny not equal to 0, then the integrating factor if is equal to 1 divided by mx plus ny. Since we were writing mx plus ny in the denominator part, it should not be equal to 0. Something by 0 is undefined, so mx plus ny has to be written in the denominator part, so it should not be equal to 0. What is my case 1? It must be a homogeneous function, and it must be a homogeneous function of same degree. If it is a homogeneous function of degree 2, then this must be a homogeneous function of degree 2. If it is a homogeneous function of degree 7, it must be a homogeneous function of degree 7. So both must be homogeneous functions of same degree, and mx plus ny is not equal to 0. Multiply m with x, multiply n with y, and this quantity should not be equal to 0. In that case, my integrating factor is 1 by mx plus ny. 1 by mx plus ny. Let us discuss this by taking a simple example. Suppose I have x square plus y square into dx plus x square minus y square into dy equal to 0. Now here m equal to x square plus y square, n equal to x square minus y square. Clearly we can understand that this is a homogeneous function of degree 2. even n is a homogeneous function of degree 2. And here when you verify for exactness, dou m by dou y is 2y and dou n by dou x equal to 2x. So both are different quantities. Dou m by dou y is 2y and dou n by dou x is 2x. Both are different. So it's a non-exact equation and both are homogeneous functions of same degree. Now let us confirm that this mx plus ny is not equal to 0. So here mx plus ny is multiply m with x. This becomes x cube plus xy square multiply n with y. This becomes x square y minus y cube. Now this is a non-zero quantity. Therefore the integrating factor in this case is 1 divided by mx plus ny and this quantity is x cube plus xy square plus x square y minus y cube. Even though it is a very complicated integrating factor, but this helps us to get the general solution of this equation. If you observe this case 1, since I am saying that both m and n are homogeneous functions of same degree, when you try to write this equation in the form dy by dx equal to f of x comma y, then this will be reduced to dy by dx equal to minus m by n. Now you can see it is a homogeneous function. It is a homogeneous function of same degree. When you combine this overall function, it is a homogeneous function of degree 0. Therefore, if RHS is a homogeneous function of degree 0, then you can handle this question by solving method 2. That is by taking y equal to bx. So one way to solve case 1 equations is by handling by method 2, or another procedure is by finding integrating factors using the formula 1 by mx plus ny. Note this. Consider a non-exact equation. Consider a non-exact equation mdx plus ndy equal to 0. Consider a non-exact equation mdx plus ndy equal to 0. Case 1. If m comma n are homogeneous functions of same degree, if m comma n are homogeneous functions of same degree and mx plus ny is not equal to 0 and mx plus ny not equal to 0, then I of is 1 by mx plus ny. Then I of equal to 1 by mx plus ny. Work out this example. This is end of case 1. Now we move to case 2. Let us see what is case 2. Suppose if mdx plus ndy equal to 0 is in the form, if mdx plus ndy equal to 0 is in the form y into f of xy dx plus x into g of xy dy equal to 0 and mx minus ny is not equal to 0, then the integrating factor I of equal to 1 divided by mx minus ny. Previous case is mx plus ny, now it is mx minus ny. Now let us focus on this form. It is in the form y into f of xy dx plus x into g of xy dy equal to 0. Now it is in the form y into f of xy dx plus x into g of xy dy equal to 0. Basically this y into f of xy is m and this x into g of xy is n. What is f? F is a function in the single variable xy. Now even g is also a function in the single variable xy. So whenever m is written in the form y into function of single variable xy and n has to be written in the form x into function of single variable xy and mx minus ny is not equal to 0, then integrating factor is 1 by mx minus ny. Now let me give clarification about function of single variable xy. Suppose I have a function f of for example x square plus y square. Now here between functions of x and functions of y there is a plus symbol. So because of this plus symbol I cannot write it as a function in the single variable xy, because between two variables x and y there is a dot symbol. But if I have function like this x square y square minus 4xy plus 9, this can be written as xy whole square minus 4xy plus 9. This we can write it as p square minus 4p plus 9. Now this is nothing but a function in the variable p. This is a function in the variable p. But what is this p? This p is nothing but x into y. Therefore, this is basically a function in two variables x and y. So we can write it as a function of x comma y. There is a lot of difference between function of x comma y and function in the variable xy. Got it? Now this is a function in two variables x comma y. But this you can view it as function in two variables x comma y or function in the single variable xy, because between powers of x and powers of y there is a dot symbol, and interestingly powers of x and powers of y are same. Here 2 2, here 1 1. That's why this can be viewed as a function in the single variable p, because I call it as xy as new variable p. Then it is in the form p square minus 4p plus 9. Then it is nothing but a function in the single variable p, where p is nothing but xy. Therefore, in order to get a function in the single variable xy, one simple point is the powers of x and powers of y must be same, and in between those powers the symbol we use is dot, multiplication symbol. In that case, you can view it as a function in the single variable xy. So whenever this happens, the integrating factor is 1 by mx minus ny. So before discussing an example in this case, write this point at first. Case 2. If mdx plus ndy equal to 0, if mdx plus ndy equal to 0 is in the form y into f of xy dx plus x into g of xy dy equal to 0, y into f of xy dx plus x into g of xy dy equal to 0, and mx minus ny not equal to 0, and mx minus ny not equal to 0, then if equal to 1 by mx minus ny. Then if equal to 1 by mx minus ny, where f comma gr functions in the single variable xy, where f comma gr functions in the single variable xy. Hope you understand this, the difference between functions of two variables x comma y and functions of single variable xy. Now let us work out an example in this case. Suppose I have an equation xy square plus y dx plus 2x cube y square minus, for example, this is 4x square y dy equal to 0. Now in this case, this is m value. What is m? Xy square plus y. What is n? 2x cube y square minus 4x square y. Intentionally, I have taken m, which contains powers of x and powers of y only, but power of y is 1 power x's when compared to x. Here x power is 1, y power is 2. Here y power n, but x power 0. But in n, powers of x are greater than 1 when compared to powers of y. X cube, y square. X square, this is y only. Because when you take y common in m, it must be a function in the single variable xy. When you take x common in n, remaining must be a function in the single variable xy. So to set up to example 2, I mean case 2, what we did is, just in m, powers of y are greater than 1 and in n, powers of x are greater than 1. So let us see. Here dou m by dou y equal to 2xy plus 1. Dou n by dou x equal to, this is 6x square y square minus 8xy. So both are different numbers. It's a non-exact equation. But what is this m? This m is nothing but y into xy plus 1. And what is this n? This n is nothing but x into 2x square y square minus 4xy. So this we can call it as y into f of p, where p is single variable xy. So this you can view add p plus 1, where p is xy. And this you can call it as n equal to x into g of p. So what is p here? xy. That means in this case g of p equal to 2p square minus 4p, function in the single variable p. Now here this f of p equal to p plus 1, function in the single variable p, but p is xy. Therefore dou m by dou y and dou n by dou x are different quantities, and m is in the form y into f of xy and n is in the form x into g of xy. Now let us confirm that mx minus ny is not equal to 0. Why we are multiplying m with x? Because in the function m, the power of x is lagging by 1 when compared to powers of y. In n, here n is multiplied with y. The reason is in n, the powers of y are lagging 1 when compared to powers of x. So to make the equal powers of x and equal powers of y, multiply m with x and multiply n with y. Therefore this becomes x square y square plus xy minus multiply n with y. So this is 2x cube y cube minus 4x square y square. Therefore this quantity is xy, x square y square plus this. So this is 5x square y square minus 2x cube y cube. Anyhow, this is a non-zero function. So my integrating factor is 1 divided by mx minus ny. This is 1 by xy plus 5x square y square minus 2x cube y cube. So hope you understand this. Work out this example. Now let us move to case 3. Case 3 is this. If dou m by dou y minus dou n by dou x equal to n into f of x. Here f of x is function of x only. It should not contain the y terms. Function of x only. Just find the difference of two partial derivatives, dou m by dou y and dou n by dou x. If the difference of these two partial derivatives is n into n is nothing but this n into f of x, it is purely a function of x, then my integrating factor is e power integral f of x dx. So if the difference of two partial derivatives is n times f of x, where f of x is function of x only, then integrating factor is e power integral f of x dx. Now even let us discuss case 4. It is similar to case 3. If dou m by dou y minus dou n by dou x equal to minus m into g of y. Here this g of y is function of y only. Then integrating factor I of equal to e power integral g of y dy. Now let us see. In case of case 3, it is e power integral f of x dx. When you simplify this, the result is only in terms of x. But in case of case 4, when you find the difference of these two partial derivatives as minus m into g of y, minus m. If you have n, it is function of x. If it is a minus m, then it is function of y. If you don't get minus, introduce two minus symbols. Introduce two minus symbols. One you give to g of y and one you assign to minus m. So if the difference of these two is n into function of x, I of is e power integral f of x dx. It is purely a function of x only. If the difference of these two partial derivatives is minus m into g of y, where g of y is function of y only, then I of is e power integral g of y dy. Now it is purely a function of y. When you look at case 1, the integrating factor is 1 by mx plus ny. It contains both x and y terms. When you look at case 2, I of is 1 by mx minus ny. It contains both x and y. But when you look at case 3, it is purely in terms of x. When you look at case 4, it is purely in terms of y. Okay? Note these points. This is the end of session. We continue examples for case 3 and case 4 in the next session. Case 3 and case 4 are very powerful for examination point of view. We continue examples in the next session. Thank you so much.